Tian, take it away with our intros.
Hi, everyone. Welcome back to Talk Math with Your Friends. Today, we have two undergraduate speakers who will be talking about their research experience. Vanessa Hernandez, a student at CSULB, who is being credentialed to be a math teacher, and Nathanael Chwojko-Srawley, a student at U of T doing research in algebra. So everyone, join me in welcoming both of our speakers, please.
Great, go for it, Vanessa.
Just share my screen.
That's how you can tell she's a professional.
Okay, there we go. My audio is good. Everything's good. Okay,
Yep.
Awesome. Alrighty, so today I'm going to be talking about my student research experience. Oh, and I'm Vanessa, by the way. So a little bit about me. I am a first-generation college student. I studied math at Cal State Long Beach, and I graduated last year. Afterward, I started working towards a teaching credential also at Cal State Long Beach because I wanted to teach math at a secondary level. And this past summer, I collaborated on math education research with Dr. Katz, and we worked on 2 papers together. It was my very first time working on undergraduate research. So today I'll be telling you all about my experience and also sharing some interesting results about what we found out. Alrighty. So first I want to talk a little bit about the difference between being a student versus being a student researcher. So there is quite a bit of overlap between these two groups, and a few skills and practices that I found carried over from being a student to being a student researcher or organization. So as a researcher, it'll look like keeping track of your data, your hypotheses, your predictions, just being very organized with your time as well. Another thing is setting goals that you want to reach, which I think many students already have experience with. Also creativity, practicing creativity. I think that research is a place that openly welcomes new and unique ideas. And lastly, attention to nuances and details. So looking for similarities or patterns or outliers in your data. And looking back, even though I didn't have any experience with research, I did realize that I had background knowledge from reading past research papers as a student. However, a difference is that as a student researcher, I had to think beyond the results that were being presented and think about other things such as what is the best way to communicate my ideas to others? How do I structure my writing? How do I best present my results? And a big difference from my experience as a student versus a student researcher is that I felt that there was more freedom and more open-endedness in research, mainly meaning that I felt that I was given more control and choice on what I wanted to focus on. So in terms of Bloom's taxonomy, as seen on the triangle on the right-hand side, I felt that as an undergraduate student, I rarely reached that top layer, the creating tier, and mainly roamed within the understanding, applying, analyzing tiers, which is a bit unfortunate, but I think it's the experience of other students as well, and it tends to be the educational model that is followed. So this reading was just something that I had to learn to get used to, and I felt more comfortable with it after Dr. Katz and I developed some themes that we wanted to focus on. But at the end of the day, it's still all about learning and collaborating and applying your skill sets and coming up with some new ideas. Okay, so then next slide. Getting into research. So like I previously mentioned, I did not have experience and I knew almost nothing about student research. I only knew what I've heard from my friends, but they were all in the sciences. So it's very different from math or math education research. But this past spring, I took the course that Dr. Katz was talking about earlier. And afterward, he asked if I wanted to collaborate on a separate project with him. I was a bit hesitant at first, but definitely curious, and I wanted to try this new challenge. And he let me know that I was already familiar with of the focus of the project from my coursework in the class, so I felt more comfortable. And I also felt very supported and encouraged, especially after BK assured me that I was qualified and that my strengths would show through in the research. So how did the research go? As I previously mentioned, we collaborated on 2 papers, both of which were based on using the Toulmin analysis in proof-based math courses. So there's a quick diagram on the right-hand side of the Toulmin model for argumentation. And the core of an argument consists of a claim, data, and warrant. So a claim is the conclusion or the statement that is being asserted. Data is evidence or previously established information. And a warrant explains why the data that you have necessitates the claim or supports the claim. And there's other pieces in the Toulmin model, such as backing qualifiers, but the core of the argument is those 3 pieces. And this is just a quick overview of the 2 papers. In the first paper, we collaborated with a 3rd author, Elizabeth Theron, who is at Pepperdine University. And this was a paper that was directed for both instructors and students who are new to using the Toulmin model in a classroom. And then the second paper, Dr. Katz and I analyzed data from video recordings of a college geometry course, and we noticed patterns in how students developed proof and socio-mathematical norms, and then related it to the Toulmin model. So the first paper was on teaching Toulmin analysis across the curriculum. So we discussed the utility of the Toulmin model in math courses for both majors and non-majors, which was Elizabeth's focus. And what was interesting about the paper was that we incorporated different perspectives. So Brian and Elizabeth offered an instructor's perspective, and then I offered a student's perspective on how Toulmin analysis helped me develop my understanding of proof. And I want to make sure that in my portion of the paper, I was relatable and that I was honest with the challenges that I found when using the Toulmin model, so that both students and instructors could see sort of what to expect based on my experience. And then one small thing that I'm kind of proud of from this work is that Dr. Katz helped me develop a metaphor for the Toulmin model. So I compared it I compared a final proof as similar to the process of constructing a physical structure and everything that goes into that. And Brian and I both like metaphors, and I think they're very fun in math, and it adds sort of a layer of depth and poeticness to your topic. So that was me sort of trying to apply some of that creativity that I mentioned earlier. And our research was inspired by 2 math education researchers, Keith Weber and Lara Alcock. And I first became familiar with their work in our spring course. After the paper was completed, we sent them our work to share it with them, and they both actually responded back and gave us feedback. And it was just going from reading these 2 researchers' work in the spring and then having them read what we came up with and respond back was super awesome. And I like to think that like a younger version of myself is very proud of that. Okay, so then the second paper that we collaborated on was focused on a college geometry course. And in this paper, we looked through video data of students developing and presenting proofs to their classmates. And we looked for notable moments where interesting discourse happened between students, but also between students and the instructor. And we noticed patterns in the students' arguments. And something that we found was that students' arguments often formed these meta layers. So they were either meta statements, where they make a larger claim about the claims in their argument, or meta justifications in their proofs. So the practice of foreshadowing is a skill that students developed over time. And this is when they sort of look ahead where they need to go. And this is them practicing meta statements, so making claims about claims. And then the practice of referencing a past technique where they were successful, and then using that to justify it being applied to something new is an example of them using meta justifications in their proofs. So what did I learn from this experience? I learned to adapt and adjust my focus according to what the data was showing, not the other way around. So sometimes I thought I had an interesting idea or a theory that was going to work out, but realized that I didn't have a good piece of data to support that. So as a result, I became more comfortable with not always knowing how my ideas were going to work out. And that's okay. And I didn't put this on here, but sometimes goals that I set worked out, but other times they didn't, because either something new came up that required more of my attention. So I would have to readjust my focus. But that was okay. I became also comfortable with that because of that flexibility and the freedom that I mentioned earlier. And I also learned to practice defining and then going back and revisiting my ideas and then refining them to be more specific. And these are some things for new student researchers to keep in mind. So be organized and flexible. And flexibility kind of goes back to things not always working out according to a plan or an idea that you may have in mind. So being adaptable helps a lot. Chunking, breaking down goals and setting goals with your collaborators really helps, just to keep you on a schedule. I think it's also very important to have a genuine interest in the project that you're working on, because you will be spending a lot of time working on it. I would also say write down any interesting thoughts and questions or ideas in a journal, just to keep track of your ideas, and then you can always go back and revisit them if needed. And then the next bullet point sort of goes back to what I mentioned earlier that I learned to do, which was defining and describing my data and my interpretation of the data with detail and precision. And then I would say ask for a second opinion and for help when needed. So look to your mentor, your professors as a support system. And this is something that I did and I often, and I think it really helped to propel my work forward. And it helped me develop my ideas more, especially whenever I got stuck, which happened often. So how to support undergraduate researchers? I would say acknowledge a student's strengths, and if you're familiar with the work, reinforce their strengths. I'm a big fan of words of affirmation, and I think they go a really long way for students. Also being aware of students' levels of experience. So like in my case, I was brand new, and I felt like sometimes I asked a silly or an obvious question, but I never felt any judgment from Brian, even when I may have been judging myself. And this ties into creating a positive and supportive environment where a student researcher feels comfortable and also feels that their work matters. And this last point is more for math education research, but I would say incorporating students' experience as a student is a very useful perspective and very useful information, kind of like how I talked about it earlier, that we did that in our first paper. And that's it, yes.
Thank you, Vanessa. We'll chat about this later, but I'm curious how you think it was different being education research versus like theory research. But after we've heard Nathanael, maybe we'll talk about that.
Sure. So hi there, I'm Nathanael. I don't have something as organized as Vanessa, unfortunately. It's been midterm season for me, so I've actually just been out of the midterm. So here with kind of an impromptu talk, I only have a couple of points that I wanted to talk about. So my talk will research more on the experience I have from school and how that related to actually doing research. What was the difference? What actually carried over? What helped me? What didn't? And what things I learned after doing researching, which makes me want to change how I approached school. Okay, let's bring up the points. So, maybe a quick side note, just a little bit more about me. So as I was introduced, I'm Nathanael, I go to U of T. I'm currently in my 4th year. I'm doing a math specialist, which if not everybody hears from U of T, that's just a math major with a couple of extra courses. And I'm hoping to pursue a graduate degree, a PhD. I actually really like learning and I really like researching. So hopefully I could do some professorial job, even if it's a teaching stream. I actually like teaching too. So that's kind of where I'm coming from. So I'll just jump straight into it. I'll start with how I saw learning, and my learning has changed after taking research, because I thought this was an interesting thing to start on. So some of my friends, and I've done this too, when I'm learning a content, you're almost learning things very often for a test or a problem set. You know, you're trying to understand the material so that once you reach the test, you'll ace your test. Now, there's maybe like multiple ways of doing this, but I realized there's actually a wrong way of doing this. And like, I was guilty of this too. Basically, like I learn things and I don't actually internalize them. And I think that's like that could be a big thing I realized that is necessary for actually doing research is when you learn things, you have to make sure that you really understand the material. If you don't, you're not actually going to know what's happening. It's like a big mistake, I think, or not a mistake maybe, but like a big thing that people don't realize how important like internalize the concepts. And what I mean by that is if you need like a professor or a student to guide you to use the concept, you don't actually know it. And I realized very quickly while doing research that there's a couple of things that I thought I knew, but like I just couldn't apply them. And I think this is like an interesting first step that I don't think everybody realizes. I remember a moment I was like we were working on a problem and like I stared at it, and one of my my teammates said like, oh, aha, this is simply this thing right there. It's this object. And I looked at it being like, how do you know? It's like, well, notice if you interpret it this way, you get that as like, how do I not see that? So I think like the first thing I want to get away from this talk is when you're doing your thing, try to make sure you really understand things. And what I mean by that is like, if you could like in your own world inside your head, like put the problem in something that you understand, your own, like, I don't know exactly what's the right way of saying this, but it's like I have like an intuitive way of seeing like the definitions I have in front of me. I don't know how much math people know here, but like there's like these concepts like groups or even like numbers or fields or the real numbers. Like there is, if you don't have like a solid thing inside in your head, I realized that like you can't go anywhere in math research because all of the math research is inside your head. Like you're not like working with like in chemistry where I could see experiments like that. It's all inside. You have to like construct your own things inside your head. So I realized that was really important. And to the matter of that, that could bring me nicely to one of my other points that I thought was cool. Right. Oh, sorry. Yeah, since it's all in your head, you're gonna actually be spending a lot of time thinking about these problems. Like I spent, I think on average, like 5-6 hours a day, just trying to think about it. And a good chunk of that is not like discovering revolutionary things. It's actually just understanding the problem. I think I spend more time like trying to like see if I could really understand what's going on than actually like coming up with things a lot of the time, which I thought was not what I expected. I thought I'll go there and I had ideas and I'll try those ideas and then they'll work out or not. But I've spent actually a lot of time like making sure my head is like in the right reality, if that makes sense, that I could actually think about the problem. And then once you're in that reality, you're really thinking about it, you're going to realize that 90% of your ideas are dead ends. And that's the next point I want to bring up. There's like a perseverance to math research that perhaps is not stated when you started it. You're not going to be there with like an idea that's like revolutionary. You're going to come up with a lot of dead ends. That was certainly my experience. I remember the amount of times I like type up the thing because we had a group chat with the professor being like, I have this idea. And then like after doing it for a day, it turns out to just be bogus, so to speak. It didn't lead anywhere. And besides like getting a deeper intuition on why that is particularly false. So I think it's important to remember that in real life, it's not like in school where there is a textbook and a solution and a finite number of possibilities for the answer, because you're given the question and you have all the material from the teacher just taught you, and he wants to or she wants to reinforce the material that you just learned. And so they're going to ask questions that will help that. So there's only a finite number of things that you could do. But when you have a research question, there is no finite possibilities because the professor is trying to tell you, this is what I'm trying to teach you. It's really open-ended. And one thing that's to the matter of open-endedness, like it turned out that like this totally different area of mathematics turned out to be useful in what we're doing. Like we were doing something in like a particular part of classical group theory. And it turned out this thing in another part of math called homological algebra turned out to be really important in like some aspects of the proof. So you realize that like having a good intuition on lots of areas of mathematics could give you like different ways of thinking that could help your thing. So I guess that's the other thing I realized in math research. And one thing that changed once I got back to school, I'm trying to like now absorb a lot of mathematical paradigms that help me think in different ways. Different courses will give you different paradigms that could maybe make you realize different things. So I personally really like algebra. And now that I'm back in school, I'm trying to do a lot of analysis because I realize it's a different way of thinking. And I want to, once I get back into research, I want to be able to see those analysis things. And the more I do analysis, the more I see things differently, which I think is really cool. And I'm applying this internalizing trick that I said at the beginning, where I try to like really make sure I understand things. I'm not going to just remember the theorem so that I could go to the test and be like, ah, yes, apply this theorem. I could like on the spot be like, oh, this is like that theorem. I could tell that this object is like this because it has the same idea. Let's see, is there any other points? Those are the two of the big things that I thought were important that I wanted to share. Oh, one more thing, or two more things. Oh, no, one more thing that I wanted to emphasize that I thought was cool was a comment that a professor once said that I didn't understand until I did research, which is actually his name is Dror Bertan, the professor, if anybody knows it. He's a U of T professor. And I once went to a meet and greet, and he says that he does research to be better at teaching. And that felt really counterintuitive. It's like, how would teaching make you better at, sorry, how would research make you better at teaching? And doing it, I think I found the answer to it, which is that while you're researching, you will realize, as I said at the beginning, that there's a lot of things that you think you know, but you realize while you're researching that you don't know, and you will get a better idea of it. And in the process of doing that, you're going to discover novel perspectives that perhaps nobody else has seen. Those novel perspectives will turn into novel questions that you could ask on your tests that students can't Google because you figured it out and you're the one person in the world who currently knows the stuff. And that actually, like some of my best profs, Dror Bertan included, and like other ones that I had, like I noticed that some of their questions were very unique, ungoogleable, completely ungoogleable. I had friends who were like avid Googlers of these things and they cannot find them precisely because these professors, they figured it out in their own research. And the way they taught the material, like some of the research professors I had like such a unique way of looking at objects because they like really got it in there. So I guess the big takeaway I had from my research experience is that what research did teach me when it comes to learning is that I really have to like internalize all of the objects that I'm working with, making sure that I understand them, learn to persevere because math is a lot of dead ends that I have to, or research was a lot of dead ends. Take the time to do that. And learn how to think in other paradigms, mathematical paradigms that could help you in problems in ways that I didn't expect. And I think that kind of covers the bullet points I had. If there's any other questions, I guess like questions are now. So that's that, and I can answer any questions.
Great, thank you.
Yeah, I hope that wasn't too rambling.
Yeah. Well, I'll stall with a question while a few more people put things in the chat to ask. So both of you thought about this connection between research and student learning, and then Nathanael, you just sort of talked a little about research and teaching. I sort of wanted to like throw that to Vanessa. So you're training to be a teacher. Have you reflected at all on ways in which you think this experience or the things we were working on would help you as a teacher?
Yeah, definitely. I think I think that the nature of the project where we were looking at video data and seeing, observing the instructor interacting with the students, and I think assessing, I've learned through that, like sort of assessing where a student's understanding is and how to move from that. So I think that's a very useful skill that I'll use as a teacher.
Mm-hmm. Cool.
I could answer a question in the chat.
Go for it.
It was by Mohanad, which was, are all math research just about getting a new proof? And I thought that was a good question because the answer is no. At least from my experience, I have an anecdote. I think that could answer this best. I have this professor whose PhD thesis was not about coming up with a new proof, but about making a particular domain of mathematics that is new and that is really scrambled with notation and some contradictions and things, make it clean, make it understandable, basically laying the groundwork for the next generation of mathematicians to work on it. And that was his PhD thesis. And he defended it successfully. He got he's now a professor. I think he's just about to get his tenure even. So it's totally doable. So I know at least there you don't have to necessarily do it, because part of doing math is not just to get a new result. It's to get a new result that people could also understand and then use that result. It's kind of useless if your result is like 600 tangled lemmas and theorems that reference 300 other papers. Like nobody's going to take that. So it's useful, and sometimes it requires actually a lot more, sometimes more, perhaps more work than the actual result itself, but it's very useful to actually take that and make it something understandable. Perhaps a good example of like the detangling of mathematics into like bite-sized things would be algebra. When algebra started, like if you look at the founding paper of algebra, which is Galois papers before he went into the duel, the way he proved things is unrecognizable to us today. Like the way he proved his fundamental theorem, what we now call like, whatever it's called again, the Galois group stuff, if anybody knows any algebra, not at all how he proved them in class today. Now it like the proof is so sleek, so simple, it just makes sense. Galois wouldn't have recognized his own proof. He'll just recognize his name. Yeah, that's another thing that Brian asked. All groups were indeed, in particular, the way we look at groups now is as axioms. People didn't look at them like that. They looked at, I don't know what's the math knowledge of people here. So I'm always hesitant to like get into like a mathy description of things. But like symmetric groups, which is just the set of all bijections, that used to be the definition of a group. That was a group. And eventually, Sylvester and another mathematician came about and noticed that there's a couple of key properties of symmetric groups that are important, and those should be the axioms, so to speak. So they abstracted it. And then Cayley came along and said, no, actually, these axioms precisely define all subgroups of a symmetric group. So it turns out that we kind of made full circle like that. So like that, and that happens in mathematics. And because of Cayley's result, now we have actually a whole other way of like looking at groups, and that generalized like crazy into category theory, into like cool things. So like math develops in another direction, but the getting to maybe not too much off topic, yes, you can do math research that's not just about coming up with proofs.
So I wanted to chime in because Nathanael, you invoked the name of Dror Bar-Natan, who his major from what I know, right, his major contribution to mathematics was precisely of this nature, right? So there's this incredible homological algebra thing called Chovanov homology that like solves all these knot problems, and you know. Whenever I've seen people give talks on this, like even you go to a talk by Chovanov who came up with this stuff, like he is going to write everything down in terms of Bar-Natan's notation. So like, you know, somehow
I didn't know that. That's cool.
Yeah. So everybody, like there's this really critical expository paper at Bar-Natan early on in Chovanov homology that like set appropriate notation and helped us think about it, and like that's how people think about it now. In a way that the original papers of Chovanov were always like, I don't know, representation theory, and it was very
was ugly.
It was not very naughty. It wasn't very topological. It was very sort of algebraic, and people couldn't get their hands on it who wanted to work with it. So yeah, I mean that can have a big impact. Exposition is super important, and thinking about things in a sort of we have for the first draft, the first version that's tricky, but now we're going to rewrite it in a more accessible way. That's absolutely crucial to the entire field.
Yeah, actually, now that you mentioned it, I can think of one more example, which I'll be brief on it to not take too much time, which is if anybody knows any algebraic geometry, when it started, when, what's his name again? The famous, one of those mathematicians at the turn of the 19th century, 20th century. When I don't remember his name, but when he invented it, everything was really combinatorial in nature. Like it was even called combinatorial topology. And a lot of the techniques that we have right now, sorry, not a lot. So he developed the math with somebody else, and it was really, really complicated. Then Emmy Northrup came around and basically said, did you know this? That you could just use my like math about modules, and this becomes like slick and clean. Because of that, like she basically founded algebraic geometry as you know it, as a consequence of her things. Like she realized that instead of looking at things as complexes and homotopy, you could look at things as homology, which is like a different way of, not to get into the details of what those are, but like now all of algebraic, not all, but a good chunk of algebraic geometry is in the language of homology because of her contribution. So it's like the math's the same. For the life of me, I can't remember the mathematician that invented it. The math is the same, but we're doing it in somebody else's language. And like now when people learn algebraic geometry, they will learn Noether's way of looking at it first, even though she didn't like invent it, somebody else did. So that's another cool example.
Vanessa, you look like you had something to say there in the middle.
Oh no, I was just reading Mohammed's question and Paul's response.
Okay.
Yeah, and I would agree that cleaning up complex thoughts is a big thing in math research. I think in math education research, it's also about utility. So making the case that this idea might be more useful than something that has been done in the past, or my mind kind of went blank a little bit.
Yeah, I definitely am. I'm a very philosophical mathematician, but as an education researcher, I'm very applied. Like I want to think about messy classrooms, and I want to think about things that help learners. And those are, yeah, cool. Catherine, if you don't mind me calling on you, I'm curious, have you done research? And if not, how do these two descriptions of research, like how do they compare to what you thought research might be like? Catherine, I was asking you as a student, I know. It's fine if this is not the good time.
Hello.
Hi.
Hi, BK. Sorry,
Hi.
can you repeat the question?
I don't know if you've done any research, but I was sort of
Okay.
curious as a student, what stood out to you in these descriptions of research? Because the faculty in here, most of us have degrees where we had to do some research, so we sort of like, oh yeah, that makes sense, that connects with me. But I was kind of curious what it sounded like to you.
So I have no experience doing research, but I recently got really interested in thinking about doing research. I think what stood out to me is finding out, like opening my mind to ways of how to I guess find out like your hypothesis or your answers. And I think another one that stood out to me is like doing research can help be an effective teacher, since I do want to be a teacher, but I don't want to be like, I want to make sure I am providing the best for the students and be overall like well-rounded and do the best I can. So I think the key part was like, oh, how the education research can help whatever I'm doing in the classroom can help like have effective teaching practice.
Thank you. I, in fact, think that teaching is mathematics research, right? In some sense, you're taking a learner's way of thinking, which is like a new axiomatic system, and you're trying to figure out what's true there and how you could deduce new results there. So I think it's in fact exactly the same activities. And so I can see why both education research and theory research would make somebody a better teacher. Lovely.
If I may add to that, when I was I did research with 2 other people, and one thing that I noticed is that people have a different set of intuitions and different set of ways of looking at things, and it sometimes became very useful to like get somebody else's look on it, because you might like, for one reason or another, there is a particular concept and you had like a convoluted way you got to it, and somebody else looks at it and somehow they got to it very quickly and they have like a nice sleek way of looking at it. And then like when you talk to them, you get to absorb their intuition that was sleek and nice. And conversely, sometimes you had something that just makes sense and they had something more complicated and you share yours. And I found that it was really useful to like speaking about like how everybody is their own like set of axioms. You said that you have to like understand. It kind of felt like in research everybody's also their own set of like theorems perhaps, or like lemmas that are different than yours, and like that could be very useful too. I found cooperation to be actually like really nice with people who are really dedicated to the same problem. There is a question that somebody asked in chat. I guess I could pick it up. It was by Ohana.
Go for it.
I could read it out loud. So it says, so in scientific fields, one can have a research about the results of an experiment, and the possibilities for experiments are a lot. Is math like that in some sense? Because you don't really do experiments with math, or does math research have more innovation? So I'm guessing, are you asking like, what is the potential amount of questions you could ask? Like in science, you're researching experiments, and in math, yeah, I see. Then I would say like, there's so many questions that you could ask. Like at first you don't see it, because I guess the best analogy of it would just be like a blindness analogy. When you're like young, or like in your life, you maybe like grew up just knowing like your room or something like that. And as you grow older, you learn that you could go out in the street, and that street connects to other streets. And it actually happens that those streets connect to thousands of streets, and those thousands of streets connect to so many cities, and those cities have airplanes, and those airplanes go to other places, and there's space. And the more you learn math, the more you realize that like space is huge. Like at first, like I feel like I remember this is like a common experience to me. I always go into a year and looking at all the math I'm gonna learn this year and being like, that's so much math. Like that's crazy. And I look at 2 years ahead and I'm like, I don't even get what the prerequisites are saying. But on the other hand, I look at the last year and I think to myself, oh, last year was fine. And then 2 years ago just feels like common sense to me at this point. And by the time I finished the year I'm looking at and look at all the math that I thought was like a huge insurmountable wall, I realized to myself, I actually like didn't really learn what I wanted to learn. I learned like this much. Like I thought I'm gonna learn like the course is called topology. I'm like, I'm gonna know topology. And by the end of it, it's like, oh, I know like this much topology. And it says like analysis, but I feel like I learned this much analysis. And there's so many questions that leaves you open. And then the more I realize that you progress in the field, you'll realize that like a lot of those questions were answered, but they'll reach a point where like people are now actively looking for the next step forward. And there's so many open branches that creates. It feels, maybe that's the same in all fields. I can't tell in physics or chemistry or anything else, but like it feels like mathematics is just a bottomless pit of like so many things that you could ask. And even while doing research in my tiny little undergraduate thing, I came across things that were just unsolved, which would have been really nice to have solved, but people are just thinking about them still. So hopefully that answers your question.
So I'd like to hear Vanessa's thoughts on it as well, because you hinted at this idea that there's like there's lots of clarifying. So do you have thoughts as well, Vanessa?
Oh, like the analogy that Nathanael made, or
yeah, or the question, either one.
Yeah, I really like that analogy that you made, Nathanael. But I think in terms of math education, you always want to improve your practice. I think as a teacher, you want to reach more students and be more effective with your teaching methods. So similar to like what Nathanael said, there's always going to be more questions, or there's always something new that is like waiting to be discovered or waiting to be incorporated in the classroom for students to learn. So I see it as that, but you don't really, I think, know like the questions that you want to ask until you're sort of there. Or you don't see what's happening until you're like the possibilities until you encounter a certain situation.
You don't know what you don't know type of thing.
Yeah, exactly.
And I think a lot of like high school people they don't know what they don't know. And so they see it as a really organized thing. But like, as you learn that organized thing, the more you learn it, you'll keep learning the super nice organized things, and you'll know what you don't know. And then eventually at some point what you know you don't know is no longer organized. And I think that's where like you start realizing the point of research. Like everything is super nice and structured until you go to that point where like you reach the end of like the nice barrier that we constructed for you called like high school and undergraduate and maybe graduate learning. And then you're now like, what you know you don't know all of a sudden becomes fuzzy.
Yeah, it can
There's
get
no
very
textbook
messy.
anymore. Yeah.
Cool. Andrew, you had a question.
Yeah, so it's not quite what you prompted us for, BK, but I'm interested in, so both of you sort of noticed that there's some differences between doing a research project and just what you do in class, right, for courses. So I was wondering if you have any ideas or inspirations about curricular sort of supports for student research, right? So like what do you think is something that you might like to have had more of or less of, or done differently, just in the course of your education that would have prepared you better for doing research?
I kind of talked a little bit about this, but whenever I read research in class, I felt like I was more focused on what are the results, what do they want me to know, similar to how sometimes we just learn something to take the test and know it. So I think it would have been useful to have maybe an exercise to think about, like take a step back and think about how is the research being conducted and presented versus just focusing on the results, which I think happened a lot in my undergraduate classes.
So maybe that's like more of the evaluation stage of the whatever that thing is called. Yeah.
The pyramid.
The Bloom's taxonomy.
Yeah, Bloom's taxonomy.
I feel like I'm when I've maybe it was just me, but when I read research, I was just trying to understand it instead of maybe analyzing it or internalizing it or doing something with it, synthesizing something new.
Now that you mentioned, I just had a thought that might be constructive to your question, which is how math differs from science, which is a lot of times in science, you learn the theorems and all that, and then you go to a lab and you prove it yourself. You know, it's like we say the ideal gas laws are this, and then you could go and you could actually like figure it out. But like perhaps one thing that's missing in math is to actually do your own experiments. Maybe because it's really difficult, maybe because there's a lack of time, I'm not sure. But like a lot of the theorems or the simple theorems, lemmas or propositions in textbooks are totally could be figured out by students. And I've seen a few textbooks that are trying to really encourage students to figure it out on their own before reading the proof. And that's probably something that's like, maybe that should be encouraged more. Maybe that's what people are trying to do with modern math education, of Moore's method and reverse classroom. But like, that's one thing that perhaps like differs between like science and mathematics, where people are forced. It's part of the curriculum to do experiments, but in mathematics, it's been more like there's so many things you have to learn to get to our stage, learn these, and then you'll figure it out later. But that's not the case in science. Like you're not gonna get to the point where you get graduates like quantum mechanics before you do your first science experiment. You're gonna do a lot before that. You get a feel of what it means to discover things, but you don't get a feel of what it means to discover things in mathematics for a very long time.
I think sort of this is related to the class I took with BK, more inquiry in a math class. You're kind of, I feel like especially middle school, high school, and even undergraduate, you're told what you need to know and you just sort of memorize it. But discovering things is a skill that I think I didn't really practice until I took a class with Dr. Katz. So I think that's maybe sort of what you're getting at a little bit.
Yeah, exactly. You don't learn how to like do an experiment in mathematics, I guess. And maybe that's people because of that don't even know what that means to do an experiment in mathematics. Because like, what does that mean? It's like, do you mean like set up a really hard integral? Is that what I'm going to try to solve? But I think people are unaware that like experiments in mathematics are really difficult to. I'm trying to come up with an intuitive example, but it's actually, I guess this is the very problem of mathematics. Like, what is a good intuitive example of that? Actually, what Brian Katz, the Professor Katz said at the beginning of equations is a good example, I think. Like, I really like that approach of like learning groups and rings. It's like we have these systems, and let's like somehow figure out like a thesis, like, and there's like maybe like 100 different things that have these ways of looking at it, can we formalize it? And it's like, okay, let's do the same thing of like 2x plus 3 equals 5. It's like, do all systems like, can you quickly like tell you what x is? Well, that's not true. There's so many things that where there's zero divisors, so that's definitely not the case. And it's like, perhaps one thing that's missing is to like introduce that what you're learning is solving problems. And a lot of the times, like a theorem is a solution to a problem. And maybe that's what many people like don't get the experience in the undergraduate. It might be easier in some courses like analysis. I find that like analysis a lot of the time, this is probably a personal bias, but like an analysis, it feels like there's like a problem that we're trying to solve, and we're going to be very meticulous about proving that this particular, like you want to find like the area of a space. It's like, okay, we're going to spend an entire semester just defining like a measure, sigma algebra, like a measurable functions, integrable functions, blah, 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 and we're going to get there. It's like, okay, now I could tell you for sure, because I was really rigorous, that this is true. But other fields might not have that, like combinatorics or number theory feels like a lot of puzzles, or algebra feels like, it's like algebra's flavor. It's like, we have this problem. Let me like axiomize this problem. Let me solve this problem in the most abstract setting, and then say like, oh, my original problem is just a special case of my really abstract thing. Like, you don't say prime numbers factor. You say unique factorizations exist and the integers are an example. So like perhaps that also could be a difference between like how different math fields will approach the problem of introducing what is like a problem that students need to solve. Speaking about like interactivity and people seeing problems and then trying to like understand why these theorems are the solutions, it might be different from field to field too.
Yeah, what we believe about the nature of the field and the learning of the field and the questions of the field and the methods of the field, all of that ties into teaching, learning, research, all of it. We have another great question in the chat, and then we might have time for one more after that, depending on how this one goes. So if you've got another big one, ask it. The question is, what was one thing that your mentors did that wasn't directly related to the math or math education that was supportive or helpful? Did you have coffee together? Do you go on walks, talk about graduate school, those kinds of things?
Well, I actually really like my mentor. The way I got into contact with him is because when I was looking for research, I was just like emailing a bunch of profs being like, do you have research? And a lot of them, but like not on the undergraduate level, sorry. And there's one person said like, well, there's this thing in my PhD thesis that I'm curious about if you want to explore it with me. And then that just like, we just like talked a lot about it. And then like, we spent a lot of time, like, I guess bonding over learning things. And I really like that. So it wasn't that, like a lot of the things that I've learned from him wasn't necessarily related to his research, but I found it was really useful to get like a good rapport with the professor, because then like you just kind of get how to vibe with them, so to speak, or at least I got to vibe with like my mentor. And that I think helped in the process of communication of him with ideas, because now I have an idea, maybe because we vibed a lot, it became easier to be like, hey, I have this thing, what do you think of that? I was less scared perhaps to present my ideas. Oh yeah, and we also went out for coffee once too, so like that very thing also happened. So it's I think it just created like an atmosphere of like, we're in here to solve a thing together. And I think that helps communication. And without, if you don't communicate, you're not going to get anywhere, I think. So it was, from that perspective, it was very useful in regards to the result that we were looking for, to have that like closeness to be able to like actually like communicate better. So that'd probably be my thought on it.
My mentor was BK. So I was a student in his class, and I think he became familiar with my work and like the level of work that I do. And I think he liked it. He would give me feedback or show it in class. So I felt more comfortable engaging in discourse with him. He also gave me, I mentioned this in my PowerPoint, but like acknowledge my strengths, because I'm someone that kind of struggles with that. So I do need that like supportive person to make me feel like, okay, yeah, you can do this. You got this. We haven't gone to coffee together because we met during a pandemic. So yeah, but we can. And no walks yet either. And he is also trying to push me into grad school. So like not push me, but nudge me into going to grad school, which I do want to do. I just need to think about it a little bit more, think about how I want to plan the next couple of years.
Excellent, thank you. I especially want you to feel like you can succeed in graduate school, which you can, so. Excellent. Well, I don't see any other questions in the chat. So let's do our little announcement of next week. I will share screen briefly. Next week's talk is called Opening the Mathematical Gates with Marian Dingle. She asked, what if mathematics doesn't belong to some of us, but all of us? What if it isn't broken, but just is not experienced as it could be? Let us think about the concept of leadership in mathematics, who is allowed through the gates of entry, and how we can actually reimagine mathematics itself. And I think that connects a little bit with some of the themes about research for today. That's been part of it, but I think this will be really powerful. And Dr. Dingle is an experienced, I think, middle school math teacher. And so I think she's gonna have some really interesting things to say, and I hope everyone joins us. And with that, can everyone please unmute and join me one more time in thanking Vanessa and Nathanael for this wonderful presentation.
Thank you.
And also Brian, one of our organizers who joined the team this fall, was a student researcher who gave a talk last year and wanted to join the team to have more content like that. And so this session was Brian's idea, and he did a lot of the work to get it to happen. So thank you, Brian, for helping us set this up. Excellent. Thanks, everybody. Great job.